Good evening, everyone. So today's class is about concept of magnetism. Okay. So in last video we have studied about Bohr's magneton, right? Minus E h squared by twice m. That's what we have learned. Okay. This is the magnetic moment due to an electron moving around a positive charge, right? Now a material is actually made up of a lot of atoms, right? So suppose this is a material, right? So there are a lot of atoms, right? So now individual atom will have magnetic moment, and a magnetic moment we represent by this a arrow, usually arrow, and sometimes we give this one, okay, magnetic moment. Now there are two types of atoms which have even number of electrons, right? Like this one, even electron 1, electron 2, even number of electrons means either 2, 4, 6, 8, this kind, or another kind is like 1, 2, 3, right? So it is odd number of electrons. Why this is important? Because usually you can say that suppose one electron is moving in this direction and this other electron may move in this direction, we don't know, right? So it can be random. So usually for an atom, a big atom, there are a lot of electrons. So which electron moves which, we don't know, and we assume that there the magnetic moment usually will cancel out, and orbital magnetic moment may cancel each other, but the spin magnetic moment, they do not cancel each other because they are almost in the same side, okay, they do not affect. So for an odd number of for an even number of electrons, if an atom have a even number of electrons, so what they may have is that they will have at least one electron that will not cancel, or for spin also they will not cancel each other. So they have a possibility that there will be a net magnetic moment. So in case of even number, net moment equal to 0, but atom with even numbers of electron, net magnetic moment is non-zero, right? So there will be a net magnetic moment. So this is the cause which creates the macroscopical magnetic property in a material, right? Now from atomic level to macroscopical property, we can divide three types of material. Okay. Number 1, diamagnetic. Number 2, paramagnetic, and number 3, ferromagnetic. Okay. So what are the differences between them? So in case of diamagnetic, diagrammatically we will understand first. So suppose this is a diamagnetic material. So there are atoms, okay. So these atoms in diamagnetic material, they are mainly have no or very little atomic magnetic moment. Okay. So, because of that they do not have magnetic field outside, they do not have. Okay. Now, if you apply external magnetic field, okay, what will happen is the field strength, okay, the field strength in diamagnetic material decreases. This is not is, should be in. The field strength in diamagnetic material, not only inside, the field strength inside diamagnetic material decreases. D-E-C-R-E-A-S-E-S, decreases, right? So, suppose its meaning is, suppose this is a material, this is a diamagnetic material. So, there is atom here. So, you put magnetic field lines here, right? This is north pole, this is south pole. If the field strength here is suppose 50 G, G means Gauss, then or Tesla you can say. So, inside this one, inside the material it will be suppose 30. Okay. So, it decreases inside it, but outside it will again be more. Why? Because many of this magnetic energy will be used up by this atom to generate magnetic moment locally in the atom. Okay. These electrons try to align themselves along the direction of the magnetic field, and because of that you get a phenomenon called your space quantization, or in your previous study you can know that if in an atom there is an electron moving in a path, so if you apply magnetic field, the electron will start moving in this plane. So, this is one plane, and then if you apply this one, so the electron will change its plane so that it become perpendicular to this field line. Okay, this happens, and to do this one, to transform from here to here, transfer from this part to this part, it has to move this angle jump, right? This is an angle theta, and because of this angle jump they need some energy. So, this energy will be absorbed from this magnetic field. Okay. I think you have heard this as ML, right? Magnetic angular momentum quantum number. This happens from here. Okay. So, now you know what is diamagnetism is that when they do not have net magnetic moment, diamagnetic material do not have spontaneous magnetic fields. Spontaneous means by themselves, do not have net magnetic moment. So, the field strength decreases inside. Okay. So, this is diamagnetism. So, number 2 was paramagnetism. Now, what is a paramagnetism? So, now in the paramagnetism you can have atoms who have net magnetic moment but they are randomly oriented. So, these magnetic moments are randomly oriented. That is why as a whole these magnetic moments cancels each other. Now you can ask me what is the difference between di and para then. So in diamagnetic, individual electron in an atom, they cancel each other, so the atom itself do not have magnetic moment, right? But in this paramagnetic, the atoms, they have a very strong magnetic moment. So number one, atoms have strong magnetic moment, right? But by combining them, their net magnetic moment is 0. Okay, but the thing is, why this happen is because they are at higher energy state. Now if you decrease the energy, if we decrease the energy by decreasing the temperature, we can align this individual atomic moments, which we cannot do for diamagnetic material. Okay, now if we decrease the temperature, how below? Every material, for every material this temperature is different. Now for a certain material, this temperature is called Tc, or Curie temperature. Okay, so above this temperature, this material will become a paramagnetic material. So usually if in room temperature the material is randomly oriented, then we will call it a paramagnetic material, right? And below, if we decrease the temperature, and they get aligned. So, okay, so suppose this is the material, okay, they are randomly oriented, the temperature is above Tc. Now everyone is aligned because the temperature is okay. Now they will have net magnetic moment. Okay. Now Curie temperature is associated with both paramagnetic and ferromagnetism. So now we will discuss about ferromagnetism. So what is ferromagnetism? So for ferromagnetism, we need to understand another concept. That concept is called domain concept. What is domain concept? Let's go in detail. So here in ferromagnetic also, they are made up of atoms, right? Okay, but here also what will happen is that they will usually, why is the difference is that the in ferromagnetic material usually atoms have very strong magnetic moment, but they are at less energy, right? Or individual atoms do not have enough energy to overcome each other attraction of this magnetic moment. It's like, suppose you have a magnet here and you have a magnet here, small magnet, you have a magnet here, Ns, this is north pole, south pole, north pole, south pole. Now they can have, individual magnet may have energy and they can be attracted by a force that also is a form of energy. They also be attracted by a force, right? In case of paramagnetic material, this force, okay, force is, the force energy is less than the individual is paramagnetic, right? But in case of ferromagnetic, what happens is that the force between this small magnet is stronger than individual energy, right? That's why what happens is that the effect of surrounding atoms they cannot neglect. Okay, so even though these also have slightly random magnetic moment,